So this is an experiment to show you how electric fields and potentials can be measured and visualized. It's a pretty simple idea. We have a tray here with some water in it, so it's a little bit conducting and will allow us to measure the potential within the water. And then we can put various things in there to determine the surfaces which set those potentials, and from those potentials we'll see the fields. In order to apply voltages, we have a power supply. Well, here's our tray, a little bit of water in the bottom of it. We have a voltmeter, which we'll look at here in a moment as a way to measure what the fields are. And we have various geometries of things we can stick in there, some probes which we'll put in the water, and some graph paper which will go underneath so you can see where we're making measurements. It's not very easy to see that from an angle like this with this camera, so I'm going to move all of this, put the water on the floor, and we'll look down on it so you can see it better, and then we'll make some measurements on it with different geometries. Before I do that, let me just point out the voltmeter. It's a standard laboratory voltmeter, so it's one that you may be familiar with already. You can go to Home Depot and get one of these things if you wanted one at home. They're not very expensive anymore. They used to be. So we have a couple of wires here. One's connected to common, and the other to the volt connection for the input on this meter, and then a dial which lets us select what it's going to measure. If I put it over here at 20 volts, then the voltage difference between the two ends of these probes is what is seen on this meter up here measured in volts. A lot of physics inside this device, good basic electronics, and so you just have to trust that that's actually what we are talking about here. It will also measure current and resistance and a lot of other things, but we're going to use it in this simple mode, set to 20 volts, and these two leads. Common usually means ground. In this case it'll be 0, and then with respect to that the red lead will be plus. In order to use this with the water, I'm going to connect this lead over to our power supply, and I'll explain that in the next part. So now we've set up this pan of water with electrodes in it. You can see I can touch the water and demonstrates it's there conducting. Underneath the pan there's a grid of graph paper you can use to measure the position of a probe. I can move around. This probe is connected to the voltmeter, and these two points are connected to the power supply, this one to 0 and that one to plus 10 volts. If I touch this, you'll see 0, but if I touch that, you'll see 10 volts. If I move the probe around, you'll see different voltages here in the conducting water. So take a look at that graph paper and decide on the coordinate grid that you want to use. I'd suggest you use X in this direction and Y in that direction. And I'll touch this probe at various places, and you can make a note of what the voltage is in these different spots. I'm just going to sample as best I can all around this area, and we'll see what we get. So let me start down here. And then I'll just go across. I'll go back again over here on the left and go across. And here and there. We know that one's 0. Here and here and there and there. We'll go up here. going up here. So we went down to and up to and back and forth this way. Let me see what happens if we go down the middle here. So I'm just going to try to find the center position. Nearly the same all the way down there. That's an equipotential. The potential is constant along that line. What if I go over, instead of being exactly in the center, go over and so I'm a half a space over from 0 here. So we'll start down here at the bottom and just go up. You see, those are not constant. So the equipotential runs straight up and down through the middle, but over here it doesn't run straight up and down. In fact, if I take that point right there, I've got 3.2 volts. Let's see if I can find another 3.2. Searching for it here. There's one right there. I'll go over here and see if I can find one. Right about like that. Here's one. Up here. Like that. Maybe around over here somewhere. In there someplace. So the equipotential near this point is a circle, or nearly so, around that point. It's not quite a circle. If you plot those out, you'll see it's not exactly the same. Let's come down a little bit farther. Maybe we'll look at this point right there and see what we have. That's 4.0. So let's see where 4.0 goes. If we go down here, it's too much. So I'm looking for 4. There's one up in here. About like that. Right in there somewhere. Right here. Over here maybe. Up here. About down here. So that 4, it's not a circle, it's some kind of a curve which comes around that way. So we've measured the potential on a grid, and now you can get a sense of how the lines might curve. See if you can take those data and figure out what the equipotential lines look like around these 2 points. Now we've changed the geometry. We've put 2 circular rings. These are actually copper rings in the water. And to make it simpler to measure, I've put a piece of polar graph paper under the tray. So we're measuring with respect to a polar coordinate system. The center of the coordinate system is now in the center of the inner ring. The inner ring is 2 inches in diameter on the outside. The outer ring is 6 inches in diameter on the inside. So if we look at the spacing between the inside and the outside, we have 1 inch from here to here. We have 3 inches from here to here. So from the inner edge there to that edge is 2 inches, and these grid marks are in half-inch spacings. You can measure even to 1/10 of a division using those grids. If I put the probe in, you'll see it measures a voltage because that's at 0 volts. and this is at 10 volts. Let's see if we can find some equipotentials. Just put it right there. 7 volts. 6.7. 7. 6.8. 6.6. Should be exactly the same, but it won't be quite. 6.7. 6.9. 7. So let's just trace out, say, where the 7 volt line is. So I'll start here. See if I can find 7 volts. Make a note of where that is on the coordinate grid. And then go over here. Look for 7 over here somewhere. Find it right there. Try it out here. It's right there. Up here. It's right there. Up here. It's right there. So it's bulging out in that upper direction just a little bit. Probably a slight difference in contact around. So up here, 7. 7. Down here again somewhere. 7 right in there someplace. So to measure the position, you can go back and look at this video as often as you want. You use the radius outward, that's the radial coordinate of a polar coordinate system, so 0 here, and as you come out, that would be 1, 2, 3. And then around in this direction, it's in degrees, so this would be 0 degrees. There's actually a scale which you might be able to read. It's 0 right there. 90 degrees here, 180 degrees up, 270 degrees over here, and these marks, the major ones, are in 10-degree increments. So that's 270, 280, 290. This is 0, 10, 20, 30, and so on. So let me just come down along a line here at constant 0 degrees. We know that on that surface, I don't want to touch it because it might move it, but it'll be 0 there. Let me just come out and I'll put it here. That's on the 1.5 mark. There. And there. I'll go back and fill in the details. I'll go halfway between those points. There, 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 and there. How does the potential vary as I go away from the origin in this direction? Let's try it over at another angle. It should be the same because it's symmetric around in this direction. It shouldn't be any different, but if there's a little difference in contact that changes the voltage on the outer circle in various places, it might be different. So we'll try it over here. There, 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 and there. It's 10 out here. I could do it on a more finely spaced grid. It would require you to be careful about grabbing off numbers and for me to be able to stay in one spot long enough, but let me just do that. I'll start right here, and then I'll move to the next grid out, next one, next one, and next one, and now I'm at 1.5, 1.6, 7, 8, 9, and at 2, and then 0.1, 2, 3, 4, 5, 6, 7, and 8. It's about as far over as I can go without touching the ring. Let's try to get one more time up here somewhere. So again, that's 0, 0.5, 1. This is 1.5 out here. So in radial distance out, we have 1 there, and then it's, okay, so and then this will be 2, and that'll be 3. So we start at 1.1, 2, 3, 4, 5, 6, 7, 8, 9, and that'll be 2. And then 2.1, 2, 3, 4, 5, 6, 7, 8, as far as I can go. Repeat it again. I'm just going to come down here in the middle where I can reach it easily. And the end of the probe, I'll put on a grid mark. So that's 0, this is 1, and I'll go to 1.1, 2, 3, 4, 5, 6, 7, 8, 9, and that's 2. 2.1, 2, 3, 4, 2.5, 2.6, 2.7, and 2.8. 0 and 10. So now we've changed the geometry again. Instead of having an inner ring, we've just got an inner point. Again, this point is at 0, and that's at 10. And if I put this in here, you can see how the voltage varies with position. So let's start out here at the middle. So it's 0 if I touch that, but if I come away a little bit, it's not. It's, in fact, if I come out here to half, it's 5.67. So I'll start at this point because I can't locate it very precisely in here. And let's just see how it varies. That's, the probe is at 0.5. And then 6, 7, 8, 9, and now we're at 1. 1.1, 2, 3, 4, 5, 6, 7, 8, 9, and we're at 2. And then 2.1, 2, 3, 4, 5, 6, 7, and 8. It'll be 10 out here on the outer ring. Inside here, there's a little meniscus around the end of that, which probably affects that voltage a little bit. And I just can't go in, but let me try. So that's on the 0.5 mark. And then that's 0.4. And then that's 0.3. And it looks like that would be 0.2, but I'm not sure. So you can experiment a little bit with whether that makes any sense. It's symmetric around this because of the outer ring being symmetric around that point. It doesn't make any difference which radius I work on, whether it's over here or there or there. It's going to be the same, so it's easy for me to reach right there. So to summarize what we've done here, we have a power supply. You can see it in this wider view now, 10 volts. And the power supply puts 10 volts on this wire, which goes over to this probe right there. And then in the middle, we have another probe, which is this one, which is at 0 volts, ground. And we have a voltmeter. The voltmeter is connected to ground. And the other lead of the voltmeter is a probe that I've been able to put into the water in various places to see how the voltage varies with position. This little pan has water in it, and we've tried various geometries, and then a piece of graph paper underneath to allow you to measure the positions of the probe, and then from those positions to find the equipotentials in this particular geometry. So we tried the circular ring with a point, circular ring with another ring inside it, and plane geometry, and 2 points.